Okay, in this class, we'll see how to find the moment of inertia for rectangular cross section of the beam, and later we'll find the deflection of the beam in case of cantilever beam, which is a special case of beam depending on the support we have used in that particular beam. Okay, let's first discuss the moment of inertia for the rectangular cross section of the beam. You can see the left hand side figure over here. So this is a particular beam. So generally L is denoted as the length of the beam, as a breadth of the beam, and D as a depth of the beam. So you can see here, if you look at the cross section, it is a rectangular cross section having this breadth B, this is denoted as B, and this depth as a D, this depth as D. And let us assume that our x-axis is passing through the middle fiber, generally which is our neutral axis, and y-axis from starting from here in this particular vertical direction. So I have denoted this coordinate axis over here also. So this is our breadth B and this is depth D. This is our neutral axis. This is our neutral axis. Now we have considered, in the last lecture we have considered a small area of cross section. Let us take this small area of cross section. This is small area of cross section, generally which is denoted by dA, and it is at a distance of, so this distance from the neutral axis we have denoted by y, because this is along vertical direction. Vertical direction is along y direction, so that's why. So if you look at the small area of cross section, this is also rectangular in shape. This length of this cross section is b, and suppose this thickness, as this is along again y direction, let us denote it by y. So if you look at small area, this would be given by b times dy, b times dy. Now we are going to find the moment of inertia for this particular rectangular cross section. Okay, so let's start from our basics. We know this moment of inertia is integration of y square, distance square, over dA, and integration over dA over area. So therefore, let me write this expression, I equals to, my y square remains same, but now area, this small area is given by b times dy. And if you see this particular expression inside the integration sign, so this we have to integrate with respect to y. So we have to put the limits on this y. And if you look at this figure, our y-axis, if you assume to be starting from this neutral axis in vertical direction, so bottom end, so this end would be y equals to minus d by 2, and this top end would be y equals to d by 2. So we have to integrate to cover entire cross section area from y equals to minus d by 2 to y equals to d by 2. Then we can integrate from this. So b, you can take it outside, and y square dy, even function, from minus d by 2 to d by 2. So I can write this as 2 times b integration from 0 to d by 2 of y square dy. So from this, if you integrate, so 2b remains, integration of y square, y cube divided by 3, integration limits 0 to d by 2. Put integration limits, you'll get a moment of inertia as this is a 2b by 3 y cube. If you put 0, anyway, it will give 0. If you put d by 2, it will give you d cube divided by 8. Divided by 8. So simplify this. So this would be bd cube divided by 12. So you have got this expression for the moment of inertia. So moment of inertia of rectangular cross section is given by bd cube divided by 12. So remember, where this b is the breadth of the beam, d is the depth of the beam, and the factor is 12 over here. So this is our neutral axis. So remember these dimensions. So actually our neutral axis is cutting the dimension d over here, depth of the beam here. So basically we are finding the moment of inertia about neutral axis. That's why this neutral axis is basically perpendicular to this dimension d. So here, how to remember this formula, basically it is bd cube, but the cube is of that dimension which is perpendicular to neutral axis. Okay, so this is brief notation to be remembered. So you have to, for the rectangular cross section, you have to cube the dimension which is perpendicular to neutral axis. And similarly, if you go for the circular cross section, I'm not going to derive this here because right now this is not in the scope of this particular lecture. And if you go and if you try to derive in similar fashion, for a case of circular cross section of radius a, let's say, so you end up by having expression pi a raised to 4 divided by 4. So this would be moment of inertia for a circular cross section having radius equal to a, and you can derive this in similar fashion. For that matter, your small cross section would be kind of this particular thing, which we have a common this particular center. And suppose if this angle is d theta and this is this 2 pi r, so if you look at this kind of sector, if you consider the whole sector, the area of sector half r square d theta, and if you integrate d theta to cover entire circle, it has to be from 0 to 2 pi. If you do all this mathematics here and integration part, you end up having your moment of inertia to be equal to pi a raised to 4 divided by 4. So this is this is the derivation for the simplistic cross-sectional area. You will further study in some kind of mechanics or somewhere else how to find this moment of inertia for different cross sections. So let's not discuss right now those points here. So again, let's move on to find the deflection in case of cantilever beam. Okay. Now, in this part of this lecture, we'll see what is meant by cantilever beam, and we'll find the deflection of cantilever beam when it is subjected to a point load at its free end. So if you look at the beam over here, so what is cantilever beam? So one of the two ends is fixed to rigid end. So cantilever beam is that beam in which one end is fixed to rigid end, fixed to rigid support or rigid end, rigid support, and other end of the beam is free. So if you look at the left end of this particular beam, this is subjected or this is fixed to this rigid support, and if you look at the other end of the beam, it is free. And now we have applied a point load W in vertically downward direction, and that downward direction is denoted by the direction of our y-axis, and horizontal is our x-axis. So x-axis, the distance along x-axis is measured from this particular point. Let's denote this point as O because this is origin, and our y-axis starts from here, but it is in vertically downward direction. For the simplicity, we have taken it in vertically downward direction because as we apply this point load in vertically downward direction, this beam is going to deflect in downward direction. So that's why, for that sake of convenience, we have assumed this y direction to be downward direction. That's it. So we have applied this particular cantilever beam at a point load with a point load of magnitude W at its free end. Now we have to find, so from the intuition we know that, so this is our fixed support. Let me draw a rough diagram how it looks after bending. So this top surface will be like this, it will bend. Bottom surface will be like this, it will bend, and this would be like this. So if you look at the middle one, so originally it was like that, and if you look at the middle point now at the end, it has deflected by this much amount. And let us denote this deflection of the end point, middle end point, means this point, let's say this is, no, let's denote it with this by some different point P. So this is P dash, and this P dash, this deflection of this point P is denoted by letter delta. All right, then now we are set up to derive this expression for the delta, which is called the deflection of end point of the cantilever beam subjected to point load acting at free end. Okay. So in the previous lecture, we have derived this relation, the famous relation sigma over y is equals to E over R radius of curvature is equals to m bending moment over cross section, sorry, moment of inertia of the cross section. Okay, so now, so let me assume any cross section. So I have assumed in this figure a cross section A dash. Okay, so we have assumed a cross section A dash at a distance x, from fixed support, because our distance will measure from fixed supports, because this is the our origin from fixed support. Okay, so what is this bending moment over here? So bending moment, we know now this is the external force W. This is going to act, and if you look at this particular cross section, so this W is, so this force W load means this is kind of force, and if you are applying this force, and if you have considered this cross section area A dash, so this W will produce certain moment about this particular cross section A dash. And that moment, how to find that moment? Moment is basically force multiplied by distance about which you are finding it. So this force and the distance of this cross section for this force vertical load is, this would be L minus X. So this L is the total length of your cantilever beam. X is the distance of cross section which you have considered. So that's why the distance of cross section from the externally applied load would be L minus X. So this bending moment would be W times L minus X. So if you put this particular expression over here, so what you get here, so let me write only this part of the formula. E over R is equals to W times L minus X divided by I, moment of inertia. Now, let me write this as a simplified version. Let me write this as 1 over R is equals to W L minus X divided by EI. Why I have written this? Because this EI is my flexural rigidity. So let's keep them together. I can call this as a flexural rigidity. All right then. Now, what is this term? 1 over R. So your deflection. So your X is the distance of any cross section, from fixed end, and if you consider Y, if you look at the direction of Y is what? Y actually denotes the direction of the deflection. So Y you can consider as a deflection. Y deflection of that cross section. Deflection of at that cross section of that cross section means how much displacement has occurred in the vertically downward direction. So for each value of X, we will have certain value of Y, because if you look at this particular here, so this would have deflected by this amount, this, suppose this would have deflected by this amount. So this basically shapes down like this would shapes down like this. So each point will have certain deflection. As in this figure, we have only denoted the deflection of end point, right? So now, how to relate this particular term? So what is this term? This capital R is the radius of curvature, and this radius of curvature, if your deflection is small, for small deflections, you can define this term 1 over radius of curvature as second derivative of your deflection with respect to your distance of that cross section from fixed support. So you can denote this or define this radius of curvature as inverse of second derivative of Y with respect to X. So I'm going to use this in this particular relation so that I get a differential equation d2y over dx square is equals to W times L minus X divided by EI. So this is what I get, and this is the differential equation. This is the differential equation for Y, and if you solve this particular differential equation, you'll get Y as a function of X. Now what is Y as a function of X? Y is our deflection as a function of X, means it depends on the position of cross section from fixed end, right? So we are going to solve this particular deflection from here onwards. So let us solve this particular deflection now. So what will happen here? So let me erase now. Now we have got this differential equation. Remember the process. You have used already derived expression from the bending moment of the beam, and now you have found this value of M based on the applied load. at certain cross section at distance x from the fixed end, and you denoted the radius of curvature in terms of derivative of y with respect to x. Now I have the differential equation. Let us solve this. So let me write this differential equation over here. So d2y over dx square is equals to w times L minus x divided by flexural rigidity EI. Now if you integrate once, integration of second derivative is first derivative. This is integration with respect to x equals to, let me write this, w upon EI. These are constant terms. W applied load constant, Young's modulus constant, cross section is fixed. That's why moment of inertia constant. So what is the integration of this particular term inside bracket with respect to x? So integration of L is Lx minus integration of x is x square over 2, and plus there would be certain integration constant C1. Now, if you look at this particular expression now, what is dy by dx? Dy by dx is the slope of y with respect to x. So this is the slope of the curve, right? And now if you see, let me draw this particular beam in the deformed shape, but let me denote only the neutral axis, how it has deformed. So it has deformed like this. Okay, originally it was like this. Now it has deformed like this. So at the end point, I have this deflection denoted by delta. Okay, all right. And this is my y direction. This is my x direction. So dy by dx is basically slope of curve, and this y is basically this deflection. So if you look at the slope of this curve, at this fixed point, it is almost horizontal. So this beam has almost remained horizontal, and we know if it is horizontal, then slope of the horizontal line is always 0. So I can write a condition over here at fixed end. So fixed end is x equal to 0. So my fixed end x equal to 0. So at fixed end, I know the value of dy by dx, that is slope, is equal to 0. Let me denote as slope, because dy by dx is basically slope. And if you look at the beam, the nature or the shape of the beam when it is deformed, it is almost horizontal at fixed end. So at horizontal end, I have slope equal to 0. Now if you put this particular values here, put x equal to 0 and corresponding dy by dx equal to 0. So what I get here? So the 0 equals to w upon EI into, this is 0, this is 0, so this is 0 plus C1. So from this, I'm able to find this integration constant to be equal to 0. All right, now we are done with this integration constant. Now what we have, putting integration constant's value 0, I am only left with w upon EI times Lx minus x square by 2. Now to find y of x, I have to integrate one more time. So if I integrate dy by dx, I get y. Again, w upon EI is a constant term. Let's not worry about that. So integration of Lx, it would be L x square by 2 minus integration of x square, x cube by 3. So it would be x cube over 6. Now there will be another integration constant, right? Because you have integrated one more time. So now you have integration constant. Now to find this integration constant, you must know the value of y for certain value of x. Look at this here, analogy. To find the integration constant C1, you must know the value of dy by dx at certain value of x that we knew, we used. And similarly, if you look at the value of y at certain x, if you look at this here, this is fixed end. So this is not going to deflect at all. This is not going to shift up and down anywhere, right? This is fixed. So at x equal to 0, my deflection y is also 0. So I can use this condition at x equal to 0, fixed end again. So fixed end is nice end, right? So y is equal to 0 because there is no deflection, because this is fixed point. There is no deflection. So if you put this condition over here, what you get? X equal to 0, 0 minus 0, this would be 0. This is also 0. So I get this C2 to be equal to 0. So these constants are not bothering us anywhere, right? So finally, I have got this relation for the y, which is deflection as a function of x, as w upon EI, w upon EI into bracket Lx square upon 2 minus x cube upon 6. Cube upon 6. So this is the expression for deflection. So if you want to know the deflection of this particular point, let us only know the distance of this point from fixed end, calculate it, put this value here, you'll get the deflection. Now, if I want to find the deflection of free end, so at free end, my distance of that free end from fixed end x is equal to length of the beam L. So at free end x is equal to L. So if I find the value of deflection at free end x equal to L, that would be W upon EI multiplied by, this would be L, put it here. So this will become L cube upon 2 minus L cube upon 6. Simplify this particular term. 3 times 6 minus 2, this 4 by 6 is 2 by 3. So this would be 2 times WL cube divided by 3EI. All right, then now we have derived this particular expression, right? So this is the expression for the delta, what we have denoted by delta here. So delta is basically the deflection of free end. So free end is nothing but x equal to L. So that's what we have derived. So delta is given by 2 times WL cube divided by 3 times EI. So look at this formula. Delta deflection of free end depends on what? It depends on the value of point load being applied, W. It depends on the value of length of the beam, L. It depends on the value of Young's modulus of the material of the beam. And it also depends on the value of moment of inertia of cross section of beam. So it depends on everything. So if you increase the load, intuitively, you know, if you put more load, it will deflect more. So it has to be more deflection. You can see this from formula. If you increase length, suppose if your cantilever is very lengthy, it's very long, right? And if you put a load here, so, you know, if your cantilever, by intuition again, I'm not talking with respect to mathematics, right? By intuition, you know, if you have certain beam which is fixed at one end and its length is more, then it will produce more deflection. If your length is very short, it is not going to produce much deflection at the free end, right? So it is intuitive. And this is not intuitive. Which point? This E and I factor. E anyway, you can see that if it is more, it is having more value of E, it will produce less deflection. So what is the more value of E? More value of E is it is kind of more stiff. More stiff in the sense, if it is more stiff, it will have more value of elasticity constant. And what is meant by stiff then? It is less responsive to the load, right? So it will try to avoid a deflection, even though if you applied more load on that particular object, right? So it is kind of more stiff. And I, it is not intuitive, because I depends on the cross section, shape of the cross section. And depending on the cross section, you'll see further that it can have different cross section, rectangular, circular, or T section or I section. And in more applications, you select I cross section of the beam because it have less deflection and all. These further things will be discussed in more lectures about some mechanics and later on about beams. All right. So in this particular lecture, we have derived the moment of inertia for the simplest cross section, which is rectangular. We have seen the formula for circular cross section as well. And then we derived the deflection of free end of cantilever beam when it is subjected to point load W at its free end. All right.